Alright, so this vector valued function is the position vector position function. I guess you could think about it like that. Again, as an object moves along a curve in the plane, the coordinates of x and y of its center of mass are each functions of time t. Rather than using the letters f and g to represent the two functions, it's convenient to write x equals x of t and y equals y of t. And so that would be the position vector. So if you can take the limit as delta t approaches 0 of that change in the function, then that would give you the velocity vector. So like if you can take the limit as delta t approaches 0 of r of t plus delta t, this is just going back to the definition of the derivative, minus r of t all over delta t. If that exists, then whatever you get from that is called the velocity vector. So take the derivative of the position vector, you get the velocity vector. And I know that the terminology is probably different than what you use in physics or mechanics, but it's basically the same thing. Position functions, velocity functions, acceleration functions. Another name for the velocity vector is tangent vector. To a curve at the point P. Which kind of makes sense because, you know, what does the derivative give you? If you take a derivative and evaluate it at a point, you get the slope of a tangent line. So that kind of ties back into why it would be called the tangent vector. What would the magnitude of the vector then be? The magnitude of the velocity vector, that's the double bars, magnitude of the velocity vector, that would be equal to the magnitude of x prime of t I plus y prime of t j. Or how do we find magnitude? That's the square root of the first derivative of x of t squared. So you'd have to square that plus y prime of t squared. Right, that's how you find magnitude. What would that give you? Physics people, that gives the speed of the object, or of an object, at time t. Similarly, what would r double prime of t be equal to? That would be the acceleration vector, or the acceleration. All right. So just to recap real quick, this is in your book. I'm just going to copy it over, show you these three formulas. This is on page 833 of your ebook. So there's velocity, acceleration, and the speed. All right, so let's look at an example. So we're going to be given a position vector, and we're going to find the velocity vector, the speed, and acceleration. All right, so our position vector is r of t equals 2 times the sine of t over 2i plus 2 times the cosine of t over 2j. All right, let's first find the velocity vector. So that's going to be equal to r prime of t, which is going to be equal to, remember this is your u here, the t over 2 is your u, your du would then be what? 1/2. So you have to say 1/2 times 2 gives you 1. So that the derivative of sine is cosine. So that's a cosine of t over 2i. And then again, your u is t over 2. The du then would be 1/2. You multiply that times the front, that would give you 1. And the derivative of cosine is negative sine, right? So it'd be minus sine t over 2j. All right, so that is the velocity vector. The speed is equal to the magnitude of the velocity vector. So that's going to be the square root of this first part squared. So what would that be? Cosine squared of t over 2. And then what is the second function? So I squared the first function plus I have to square the second function, and the second function is negative sine t over 2. So negative sine t over 2 times negative sine t over 2 is positive sine squared t over 2. And that is the Pythagorean identity, right? So that's just the square root of 1, or just 1. All right, so the speed is 1. And what about the acceleration function? Or, I'm sorry, vector. That's going to be, the derivative of the velocity vector. So that's going to be r double prime of t, or, now this time your u is t over 2, your du is 1/2, so you have to multiply the front by 1/2. So that's going to be negative 1/2 sine of t over 2i. And then the derivative here, again, you have to multiply times 1/2 in the front, so that's going to be minus 1/2 cosine t over 2j. Now, look at the velocity vector. The velocity vector, if you think about a particle that moves in that motion or direction, let's see. Could we take the original function, the position vector, and then see what that would be in rectangular? Because this isn't rectangular. This is like, you know, parametric equations. If we took this and we changed it over to rectangular, then that would be, by eliminating the parameter, then that would be equal to x squared plus y squared equals 4. You do that by using the, you know, x squared plus y squared equals 1 and plugging those in and squaring them and then multiplying everything by 4, and you get this. And what is that, what would that look like graphically? Circle, right? So here is a graph of that position function. This equation and this equation, same thing. So that curve, that position vector that we started with, is a circle of radius 2 centered at the origin. Now think about the velocity vector. Here's the velocity vector here. All right. So as that changes with respect to t, you know, because t, that would be what, like time? It's going to go around the circle in a clockwise rotation at a constant speed. Your book says the position vector has a constant magnitude but a changing direction as t increases. The particle moves around the circle at a constant speed. I don't know if that makes sense. So we didn't really evaluate anything there. Let's do one more similar to that. And then we'll probably move on. Like I said, I'm not going to spend a lot of time on this because this is physics. Even though everybody in here hasn't had, you know, engineering physics, this is not just engineering physics. This is regular physics 1 type stuff. It's just, it may have been called something different in your physics classes. Most of you have had at least one. Alright, so let's say that we have this position vector. I know it's a position vector because I have r of t equals. Let's sketch the path of an object moving along this plane curve. And we're going to find the velocity and acceleration vectors t equals 0 and t equals 2. Alright, so to sketch this and for it to make sense in my brain, I have to change this over to rectangular. So how do we do that? We have to eliminate the parameter, right? So we have x equals t squared minus 4, y equals t. You see where I get that from? There, there. So what's my function? X equals y squared minus 4. You just plug in y for t, right? Because y equals t. So does anybody know what shape that is? Of course, right? It's a parabola. Which way is that parabola opening? Upward or downward?
What did you say?
Which way is it opening? Upward or downward or left or right? Or was it through? Right. Right, because if it was y equals x squared, it'd be opening upward. If it's x equals y squared and the y squared is positive, it opens to the right. Okay. So what is the x-intercept? -4. What is the y-intercept? Plus or minus 2. I'm just letting x equal 0 and y equal 0. I'm not doing any magic. Alright, so it's going to kind of look like this. Alright, if I want to figure out the velocity when t equals 0 and t equals 2, then I need to find the velocity vector. Since I've sketched it. So the velocity at any time is going to be, so v of t is going to be equal to r prime of t is going to be equal to what? 2ti plus 1j. Alright, what about the acceleration vector? So the acceleration vector is going to be equal to the derivative of the velocity vector or the second derivative of the position vector. So that's going to be just 2i, right? Because the the derivative of 1 is 0, so that component goes away. So now I can evaluate these. I can evaluate v of 0, that's equal to r prime of 0, which would be equal to what? 1j. And I can evaluate a of 0, or remember that's the second derivative evaluated at 0, which would be, there's nothing to plug it in for, so it'd be what? Just 2i. Right, if I plug it in right there, there's nothing to plug it in for. Now, let's do the same thing for 2. V of 2, that will be the first derivative evaluated at 2. That will be equal to 4i plus j. And then acceleration at 2 is equal to the second derivative evaluated at 2 is still just equal to what? 2i. So I'm going to put a little graph up here that's very similar to that graph, and I'm going to read you something out of the book about this graph and, you know, kind of compare it to what we had there. All right. So this says, referring back to our graph, for the object, and this is back at our graph up here, for the object moving on this path, Note that the acceleration vector is constant. See that? Acceleration doesn't change. It's not dependent on the time. This implies that the speed of an object is decreasing as the object moves toward the vertex of the parabola, and the speed is increasing as the object moves away from the vertex of the parabola. All right. Now, this is very similar to what we were just looking at. This type of motion is not characteristic of comets. That travel on parabolic paths through our solar system. For such comets, the acceleration vector always points to the origin, or the sun, which implies that the comet's speed increases as it approaches the vertex of the path and decreases as it moves away from the vertex. And why would that be? Maybe due to gravity. Right. Oh, gravity. Death, taxes, and gravity. 3 things you can count on. If we could only manipulate gravity waves, we could only see, view gravity waves. But then if we could only manipulate those, that'd be awesome. So that's how you fly, Justin? All right. So that's about all I want you to be able to do. Just find velocity functions, or velocity vectors, speed, and acceleration vectors. And then maybe evaluate them at points. So it's not anything too terribly complicated. But remember, if you take the derivative of, like here, take the derivative of 2t, you get 2i, but then the derivative of 1j, you get 0j. So it goes away because there's a constant there. All right, the next section is on tangent vectors and normal vectors. This is 12.4. First thing we're going to look at is the definition of a unit tangent vector. Like a unit vector, a unit tangent vector. You could probably guess the formula that you have to use for a unit tangent vector if you think about a unit vector. All right, so here we're going to let the unit tangent vector be capital T of t. That's equal to, well, how do we find a unit vector? Remember, it's going to end up being r prime of t over the magnitude of r prime of t. Yeah, that's the way the book uses it. Capital T of t. Don't like it. I don't like that notation, but just kind of deal with it. Dr. McCone, me and him have had some conversations about trying to come up with a uniform notation, but there hasn't been any traction there because I think he wants to change it all to physics notation and then we just use all that, but that's just not the way things work. I'm fine with meeting halfway, but he's like my way or the highway type of.
He's like, I'll go one, you go 99.
See, you just wait till he retires, and when the next one comes in, you say, well, me and Dr.
Yeah.
We
We
decided to switch off.
decided to use all this math notation, right? I don't care what your engineering classes are going to use. I really wish that I'd get some engineers in here and see, and they'll probably be like, notation doesn't matter. We have to do it all anyway, if I had to guess. But just to see what they're using. All right, so let's say that, for example, so how would we find a unit tangent vector if we're given a position vector. So find the unit tangent vector for r of t equals ti plus t squared j when t equals 1. Now we can come up with a general formula, but to actually get the vector out, we have to let t equal something. Alright, so we need to find the derivative of the position vector to get the tangent vector. Remember, it was called the velocity vector or tangent vector. So that's just going to be 1i plus 2tj. Now, what's another way I could write that? I'm not. If you watch this, like somebody else teach this, or a physics person teach this, they would do this here like this. Actually, it'd be what, 1 and then 2t. Now, if you see something like that written, it means the same thing. So don't freak out. I'm not going to write it like this right now, but if you did see it, just know it means the same thing as 1i plus 2tj. Just another way of writing it. All right. So we have our r prime of t. That's this right here. Now we need to find the magnitude of r prime of t. So that's going to be the square root of what? 1 squared plus 2t squared. Or the square root of 1 plus 4t squared. Don't forget to square the 2. Common mistake. Alright, so my unit tangent vector without plugging anything in, capital T of little t, is equal to 1 over the square root of 1 plus 4t squared times I plus 2tj. And you might see this written in the numerator, but this is kind of related back to the notation that we used whenever we found unit vectors. It's really this times this, but it means the same thing if I write it in the numerator or not. So what would the unit tangent vector be equal to when t equals 1? That's capital T of 1 would be 1 over the square root of 1 plus, it's going to be 4 times 1 squared, so 1 plus 4 times I plus, and then that would be 2j. You could. Yes, you can. It's not wrong to do that. I guess because this part's gonna be a constant, that may be the reason why they kind of separate it like that, but it's okay to write it in the numerator as well. Alright, so graphically, what would that mean? So I'm going to show you what the position vector looks like. You could say x equals t, y equals t squared. So that means you would have y equals x squared. I think I just did a bunch of that in my head, but you understand what I'm talking about? Look back at the position function or position vector. Here's the position vector right here. So if this right here is x and this right here is y, then you could have y equals and then plug in there x squared. So that's why it's that parabola there. And so if you find the tangent vector of that position vector and you evaluate it at 1, that gives you this tangent vector here.
So what is that big T again? What is that?
The big T stands for the unit tangent vector. What would that be? That would be a tangent vector that has a magnitude of, if it's a unit tangent vector, wouldn't that be a magnitude of 1? That's a really important concept too. That unit of 1, or its magnitude equaling 1, because if you multiply that times a regular vector, that gives the direction to whatever I say multiply, like if you take the cross product and things. That's why we have to use unit vectors to do all of that, sometimes in formulas to give something a direction. Because it's like multiplying by 1, but it's not really multiplying by 1 because it's a lot more complex than 1, but it's like multiplying by 1 because it only has a length of 1. And it just gives something else a different direction. All right. So unit tangent vector. What is the unit tangent vector? It's a tangent vector of 1 unit. The tangent line to a curve at a point is the line that passes through the point and is parallel to the unit tangent vector. Again, the tangent line to a curve at a point is the line that passes through the point and is parallel to the unit tangent vector. The tangent line to a curve at a point is the line that passes through the point and is parallel to the unit tangent vector. Let's just look at this example, example number 2 here. I'm going to pull that up. Let's just read through it. Finding the tangent line at a point on a curve. So this says we're finding the unit tangent vector and then find a set of parametric equations for the tangent line to the helix given by. So this is in 3 dimensions. So our position vector has ij and k. And if you remember, we did look at an example of a helix. I guess it was a few weeks ago. So to find the unit tangent vector, it follows the same formula. Alright, so it's r prime of t over the magnitude of r prime of t. So you do that. This part right here, why is that equal to 4? Because it's 4 sine squared t plus 4 cosine squared t. Right, so you could factor 4 out and use the Pythagorean identity and get 4 times 1. So you get 4 for this, and then plus 1 is square root of 5. So the magnitude's the square root of 5, so it's 1 over the square root of 5 times the derivative of r of t. So then you could plug in. It says at the point square root of 2 pi over 4, t equals pi over 4, and the unit tangent vector is, alright, why is t pi over 4? I mean, this is 1k.
Up at the position.
Up here?
Isn't there something above that? Or just RT?
So,
So the point was pi over 4 for k,
yeah,
then t would have to equal pi over 4.
yes. And so if we plug it in here, here, and then there's nothing to plug in there. The sine of pi over 4 is square root of 2 over 2. Cosine of pi over 4 is square root of 2 over 2. Of course, those 2's cancel out. And we're left with this. This is our tangent unit vector evaluated at this point. And this says using the direction numbers, A equals -2, negative square root of 2, B equals square root of 2, and C equals 1, and the point, square root of 2, pi over 4, you can obtain the parametric equations. It's been a while since we've done parametric equations. Remember, they have a formula, though. So it's x sub 1 plus as, I think we used t before, at. It's what we used when we first went over parametric equations, but it's just a different variable. So that's square root of 2 minus square root of 2s, then y sub 1 from this right here, plus here's bs, and then z sub 1 plus cs is just pi over 4 plus s. Alright, and you can look here at this figure. It says this tangent line is shown in figure 12.21. That's this figure here. So this tangent line here, these are the parametric equations that would give you that tangent line. In example 2, that's the example we're looking at, there are infinitely many vectors that are orthogonal to the tangent vector t of 2. And what's orthogonal mean? Perpendicular. There are infinitely many vectors that are orthogonal to the tangent vector. One of these is the vector t prime, capital T prime of t. This follows from property 7 of theorem 2.1. That is, I'm not really worried about this, but let's just keep going with it. Capital T of t dotted with capital T of t equals the magnitude of t of t squared equals 1. Dot something with itself. But then here it says that implies that t of t dotted with, t of t dotted with t prime of t equals 0. And that makes sense because it's orthogonal. Yeah, if you do the dot product of two vectors and you get 0, then it's orthogonal. So if you take the unit tangent vector and dot that with the derivative of the unit tangent vector, then you get 0. So that goes back to saying here that there are infinitely many orthogonal vectors to the unit tangent vector. It says and remember I told you normal is another one of those words that means perpendicular. It says by normalizing the vector capital T prime of t, you obtain a special vector called the principal unit normal vector. So the principal unit normal vector, which it says that the principal unit normal vector is capital T prime of t over the magnitude of capital T prime of t. So what was capital T of t? Remember what that was? The unit tangent vector. So this would be the derivative of the unit tangent vector divided by the magnitude of the derivative of the unit tangent vector. No, it's not bad at all. It's the same notation. This is called the principal normal unit normal vector. I would like to know what this is called in physics. I mean, So, anyway, that's where we're going to end today.
What $1.4 was it though?